In the previous videos, we defined equilibrium in terms of the maximization of entropy. What I want to show in this video is that we could also define equilibrium in terms of the minimization of energy. Right? This is going to be equivalent to the entropy maximization definition. So we're going to show how these two definitions are related to one another. Right, and so what I'm going to do first is let's define an entropy function that depends on the independent variables u, v, n, so internal energy, volume, number of molecules, and that it also depends on some property psi. So I'll just call this some property or some sort of internal constraint. Okay. And so based on what we saw before, we know that at equilibrium, the equilibrium psi value would be determined by the entropy maximization sort of relationships, such that ds d psi at constant u, v, and n, that would be equal to 0, right? So that's an extremum. But since we're dealing with a maximum, we also know that the second derivative would be negative. Okay? All right, so that's just, what the entropy maximization sort of idea says. What we're going to do now is we're going to recast these relationships in terms of internal energy. So we'll have an internal energy function that depends on entropy, volume, n, and psi as well. Okay? And so what we're going to do is we're going to take the partial derivative of internal energy with respect to psi at constant, v and n, but what I really want to focus on is the constant entropy part. Okay? So I'm just leaving off the v and the n just for brevity. All right, so what we want to do is we want to evaluate this partial derivative. And so to make this analysis easier, I could recognize that we have some sort of unmeasurable property down here. And so we could rewrite this partial derivative in terms using the triple product. So using that triple product rule, we could rewrite this partial derivative like this. Okay? All right, and so based on the triple product rule, we get these two partial derivatives. For this partial derivative in the bottom, we have ds du, and we know from our basic properties of entropy that this is just equal to 1 over t. And so we get that from the triple product rule, we get this relationship. Okay? And by inspection, we see we have this partial derivative now, and we know that at equilibrium, this partial derivative is equal to 0. And so as a result, we find that du d psi, constant s, is also equal to 0. Right? And so we find that if we're minimizing energy, the partial derivative of that energy with respect to this variable also gives us some sort of extremum. Now the next step, in order to determine that at this extremum the energy is minimized, we need to take the second derivative. Okay? So if we'll take the second derivative of energy with respect to psi, a constant s. Alright, and so what we're going to be doing is we could expand out, essentially, we could plug in this sort of relationship into here. Okay? So if we go through with a second derivative, we get this. Okay? du ds psi constant s du ds psi, and this is d psi ds d psi u constant s. Okay, so just to kind of clarify, what I'm doing is, imagine that I flip this up, and so this was just this derivative was just the product of ds d psi times du d psi, right? And so when I take the second derivative, I take the derivative of that product with respect to psi. And so as a result, I need to perform the product rule here. Okay. All right. So, by doing the product rule, we could get out this sort of derivative, and we could simplify it, because immediately I see I have ds d psi, and I know that by definition that's equal to 0. So this whole first term goes away. For the second term here, I have du ds, and once again, using our entropy relationships, we know that this is equal to temperature. Okay? Now, to figure out this term, what I need to apply is the expansion rule. Okay? Alright, so if I apply the expansion rule, ds d psi, this one's constant u, this one's constant s. I apply the expansion rule, and I get this. du d psi constant s plus d psi ds d psi d psi constant s. Okay. Here, this one's just 1. That's fairly straightforward, right? And we know that this one, based on this relationship up here, that this is 0. So that first term goes away. And so what we're left with here is essentially the second derivative of this function. Okay? So now that we know that this only leaves us with that, I'm going to write out, I'm going to go back to this expression here. So we have d second derivative of u with respect to psi at constant s, and what we're left with is the t from up here, negative t, and what we have is d psi ds u, or in other words, we have negative t the second derivative of s with respect to psi at constant s. Or I mean constant u. Okay. In fact, actually, I think this one should be a u up here. Okay. All right. So we have this sort of relationship. And if we go back here, we know that this, by definition, the second derivative of our entropy with respect to psi is negative or less than 0. Okay? And so because we're multiplying this by negative, this tells us this is greater than 0. And so we get that the second derivative of energy with respect to psi is greater than 0. So this tells us that the energy is at a minimum. Okay? All right. And so the point of this exercise was to show that our definitions for equilibrium, which were based on entropy before, equivalently we could also base them around energy. And so what this is telling us is that according to the second law, it shows that at equilibrium, the internal energy is minimized at constant entropy, volume, and molecule conditions. So this definition is equivalent to the entropy maximization definition.